In this video, we will be looking at both scalar and vector projections. And before we get into scalar projections, we're going to do a little investigation. So we have vectors A and B, and the magnitude of vector A is 3 units and the magnitude of B is 5 units. When vector B is drawn horizontally and the vectors are placed tail to tail, they form an angle of 60 degrees. So let's draw that setup. Here is vector B, drawn horizontally. It has a magnitude of 5. Vector A is a little shorter. It has a magnitude of 3. And when the vectors are placed tail to tail, their angle is 60 degrees. Now we are told, imagine a sun directly above the vectors. Vector A is covering part of vector B, so a shadow would be formed. Highlight the shadow cast on vector B in your diagram and what is the length of that shadow. So imagine the sun right above vector A. And when it's right above, this vector here, vector A, is going to cast a shadow straight onto vector B. That shadow will be this length here, part of vector B. Now, how am I going to calculate it? Well, when that shadow is cast, we have now created a right triangle. And in that right triangle, we have the angle 60 degrees. The shadow is adjacent to 60, and the 3 is the hypotenuse. So we are just using SOHCAHTOA, and specifically the cos ratio. So cos 60 is going to equal our shadow divided by the hypotenuse of 3. So the shadow will be 3 times cos 60, which is approximately, or actually exactly equal to 1.5 units. Now that shadow that we just calculated, that is actually the scalar projection of vector A onto vector B. So how much of vector A covers vector B? And the notation we use is scalar proj, or scalar projection. And then we have our vector that is casting the shadow, if you will. And onto what vector is it casting a shadow? Vector B is the subscript. All right, can you generalize a formula for this scalar projection? Well, the vector that is casting that shadow is always going to have the hypotenuse, and the shadow will always be the adjacent side. So the scalar projection of A onto B is going to be the hypotenuse, and the hypotenuse is the magnitude of A, times cos of that angle. And then that is the calculation that will give us that adjacent length. What about if it was flipped around? The scalar projection of B onto A. Well, if that happened, so B onto A, now vector B is acting like the hypotenuse. It's the one that is casting a shadow on vector A. So the magnitude of vector B is the hypotenuse. The shadow cast on vector A is the adjacent. So we're still doing our cos ratio. So the magnitude of vector B times cos theta. Now, this magnitude times cos of an angle kind of looks like the dot product with a missing element. We know this as our dot product. The dot product between vector A and B is the two magnitudes being multiplied and then multiplying that by cos of their angle. Well, let's say I wanted to write the scalar projection of A onto B. I can use the dot product definition. The scalar projection of A onto B, we've already established, is just the magnitude of A times cos theta. So why not just divide both sides by the part that we don't need? So this is what we have now. The scalar projection of A onto B is equal to, we already know, the magnitude of A times cos theta, like we saw in our diagram. And with manipulating our dot product, it's also equal to the dot product between A and B divided by the magnitude of B. The version of the scalar projection formula that I use is going to depend on if I'm given the angle or not. Do I have geometric vectors where I have the magnitude and the angle, or do I have algebraic vectors where it's easier for me to calculate the dot product and the magnitude? So let's make some conclusions here. So visually, when I'm going to do the scalar projection of A onto B for all three of these examples, and I'm going to draw in what that scalar projection would be. In the first example, the angle between A and B is an acute angle. And when A is projected onto B, we draw that perpendicular side line, and here is the scalar projection. When A is projected onto B and we have a right angle, well, vector A is already perpendicular to vector B, so that scalar projection would be 0. There is no shadow cast, okay? Also, if you think about it in terms of the formula, if the angle is 90 degrees, cos 90 is 0. So our scalar projection will be 0 there. And finally, if our angle is obtuse, then the scalar projection is actually going to be behind vector B. So if I were to extend vector B backwards, the scalar projection, when I drop a perpendicular line to the extension of vector B, the scalar projection is behind vector B. So what does the scalar projection actually tell us? It tells us how much one vector is projected on another. So how much of vector A is on vector B, okay? And we've already stated our two formulas right here, one using basic SOHCAHTOA and one manipulating that dot product. So let's try using those formulas on this next example. Given the magnitude of vector A is 10 and the magnitude of vector B is 16, and the angle between them is 120 degrees, find the scalar projection of A onto B and B onto A. And I'm going to start with a sketch. So I'm going to put vector B here. Its magnitude is 16. Vector A is shorter, and the angle is 120 degrees. All right, if I want the scalar projection of A onto B, this is what I'm solving for. It is going to be a negative scalar projection because the angle is obtuse and cos of an obtuse angle is a negative number. But our scalar projection of A onto B is going to equal the magnitude of A times cos of that angle. So that's going to be 10 cos 120. And we get -5. So negative just tells us that it's behind the vector, and 5 gives us that actual distance that A is projected onto B. Now, if we go in the other direction, if I want the scalar projection of B onto A, now vector B is acting like the hypotenuse, so we need its magnitude times cos of the angle. Now I'm just going to go to my visual here and I'm going to project A backwards, and if I draw a line that is perpendicular to vector A starting from the top of vector B, then here is that scalar projection. 16 is the hypotenuse, my projection is the adjacent side. So now we want the magnitude of B is 16 times cos 120. And again, I'm going to have a negative number here, and it's -8. And that's how much of vector B is projected onto vector A, so that's how much of a shadow vector B casts on vector A. And let's try an algebraic vector version. For this one, we're given vector V, which is 2, -3, 4, and we want to find the scalar projection of V onto, first we're going to find it onto vector U. Well, I'm not given any information about the angle here, which means I have to use the dot product definition. Now, this isn't something that you need to memorize, okay? I'm going to write the dot product and I'm going to recreate the scalar projection formula for us on the spot so that it's not some new formula I need to memorize. The dot product between u and v is the magnitude of u times the magnitude of v times cos theta. If I want to do the scalar projection of v onto u, then I know ultimately I need the magnitude of v, that's going to be the hypotenuse, and cos of the angle. Which means, looking at the dot product, what is it that I have to divide out? The magnitude of u. So this is what I'm going to use for my scalar projection. I'm going to use the dot product and divide it by the magnitude of vector u. So let's see, the dot product. 2 times 3 is 6. Negative 3 times negative 1 is positive 3. And 4 times 0 is 0. So I am adding those products. Remember, dot product is scalar, so that will be 9. And that's going to be divided by the magnitude specifically of vector u. So taking the square root of 3 squared plus negative 1 squared plus 0 squared. So 9 for the dot product. Then we have the square root of 10. And to be in nice proper form here, I'm going to do 9 root 10 over 10. And there's the scalar projection of vector v onto vector u. All right, next, the scalar projection of vector v onto the z-axis. Now, the z-axis, I'm going to use the unit vector k for that. Now, what is the unit vector k? 0, 0, 1. So when I do my scalar projection formula, I know I'm going to use my dot product. So I need to take the dot product between v and k. And what am I going to divide out? Well, thinking here, the scalar projection of v onto k would be the magnitude of v times cos theta, which means I would ultimately divide out the magnitude of the unit vector. Well, that's easy because a unit vector has a magnitude of 1, so I don't even have to think about that. Now I can just take the dot product between unit vector k and vector v, and that's going to be great because the x and y components are 0 for unit vector k, which means I don't care about multiplying 2 with 0 or negative 3 and 0, because that's just 0. All I have to do is 4 times 1, which is 4. So our scalar projection of v onto k is 4. All right, let's add a tiny little bit onto scalar projection by making the scalar projection into a vector instead. So before we get into that, let's just recap a little bit on unit vectors. So let's say that the length of a line segment is 8 units. If I want a vector to have the same direction as vector v, but have a magnitude of 8 units instead, how can I represent this vector? Now, if I want the direction of v, but I need the magnitude to be 8, a good starting point would be, let's get the unit vector that follows the direction of vector v. And then once that's a unit vector, my direction part is taken care of, and then I can just multiply that vector by 8 to get a magnitude of 8 instead. So let's start with getting the unit vector. If I want the unit vector of vector v, I'm going to have to take vector v and multiply it by the reciprocal of its magnitude. Because anytime you take a number and multiply it by its reciprocal, you get 1. So what is the magnitude of vector v? Well, we have 4 squared plus negative 2 squared. That's going to be the square root of 20, which can be simplified to the square root of 4 times 5, which is 2 root 5. Okay, great. So the unit vector v is going to be the reciprocal of that magnitude, times the vector itself. Now, before I distribute that scalar in, because that's what it is, I am going to rationalize the denominator, and I'm going to multiply top and bottom by root 5. So then we'll have 2 times 5 on the bottom, which is 10. That looks better. And now I will multiply that into my vector. So that will be 4 root 5 over 10, but 4 over 10 reduces to 2 over 5. And then negative 2 root 5 over 10, but the 2 over 10 reduces to negative root 5 over 5. So this now is a unit vector, and I haven't changed the direction at all because I just multiplied the vector by a scalar. So these are collinear, it's just now I have a vector that has a magnitude of 1. So now if I need this vector to have a magnitude of 8, I'll just multiply this unit vector by 8 instead. So I'll have 8 times 2 root 5 over 5, and 8 times negative root 5 over 5. And what will that clean up to? 16 root 5 over 5 and negative 8 root 5 over 5. And now we're ready to go. That vector here follows the direction of vector v because it's just a scalar multiple, and it does have that magnitude. And you can always do a quick Pythagorean theorem to double check that the magnitude is in fact 8. So how does this relate to a vector projection? Well, the calculation for the vector projection of A onto B is just the corresponding scalar projection of A onto B multiplied by the unit vector in the direction of B. So I want the magnitude of the scalar projection, but I want the direction of vector B. So visually, what is that? Here's vector B. Here's a random vector A. Projecting it downwards to cast that shadow. This is the scalar projection. If I want it to be a vector projection, I just need to add a direction onto it. So I need that direction of B because the scalar projection is on vector B. So I need the direction of B, but I need it to be a unit vector so that that unit vector can be multiplied by the actual scalar projection, so the magnitude, the length of that piece. So what is that going to look like? The vector projection of A onto B. Well, we said we need the scalar projection. So the scalar projection is A dot B divided by the magnitude of B. But then that needs to be multiplied by the unit vector that follows the direction of vector B. What did I say here? I can turn any vector into a unit vector by multiplying it by its reciprocal. But I'm just going to do the multiplication. So vector V times 1, I'll just put that on top. And then in the denominator, I'll have vector V. But in terms of the direction we're dealing with. So vector B over the magnitude of vector B. That is the unit vector. And if we clean this up, so like if I do the magnitude of B times itself, I can just write the magnitude of B squared, or using the magnitude property, we know that that is also equivalent to the dot product of B with itself. So you have different ways to get that scalar value that is in front of vector B. So one way is A dot B divided by the magnitude of B squared, and then that's your scalar that you multiplied the direction by. Or you can just treat it all in terms of dot product, A dot B over B dot B times the magnitude. And this portion here is all scalar. Okay, so let's give that a try. Given vectors A, B, and C, find the vector projection of A onto B. All right, vector projection of A onto B. I personally like the dot product definition of that vector projection. So A dot B over B dot B, okay? And that covers the scalar projection plus converting vector B into its unit vector. And that will be multiplied by vector B because that's what the projection is on and following the direction of. And now, the dot product between A and B. 3 times negative 1, 1 times 1, negative 2 times 4, all over the magnitude of, or the dot product of B with itself. So negative 1 times negative 1, plus 1 times 1, plus 4 times 4. And that will get multiplied by vector B. So what do we have? We have negative 10 over 18 times vector B, which I am going to reduce. It's negative 5 over 9, and vector B is negative 1, 1, 4. And that will just be, two negatives make a positive, so 5 over 9, negative 5 over 9, and a negative 20 over 9. So there's the vector projection of A onto B. This vector here has the magnitude of the scalar projection, but because this is just a scalar multiple of vector B, it is collinear to vector B, so it's following its direction. But actually, if we take a closer look here, vector B had a negative, then two positives, whereas the vector projection is a positive and two negatives. So it's actually going in the opposite direction because the scalar projection must have been negative. So the angle between A and B must actually be obtuse. All right, let's try the next one. We want the vector projection of C onto A. So what's that going to look like? I need the dot product between C and A. And then on the bottom, we have A dot A. And we're following the direction of A because we're projecting C onto A. Now, let's say again, you forget the formula. That's okay. Go back to your dot product. So let me start this as if I've completely blanked, and let's recreate it before we actually do any calculations. I'm going to start with a dot product. We're talking about vectors C and A, so I'll put their dot product. Now, if I want the scalar projection of C onto A, I need vector C, that would be the hypotenuse, and cos theta. What I've circled, that would be the scalar projection, which means I would have to divide out the magnitude of A to cancel those out. So this here represents the scalar projection of C onto A. Now, if I want to make this a vector projection, this just has to be multiplied. So here's the scalar. This just has to be multiplied by a unit vector going in the direction of vector A because we're projecting onto vector A. So that would be the reciprocal of the magnitude times the vector itself. And look what we have here. The magnitude of A times itself, that's just the magnitude squared, which is just the dot product of vector A. But again, if you don't like using the dot product of A and A for the denominator, you can just find the magnitude of vector A and then square it. That's perfectly fine. But this will take us here. So this is not a new formula that you need to memorize. If you can visualize the vector projection and you remember your dot product, that is all you need. You can recreate this at any moment. So let's do the vector projection of C onto A. I am just going to rewrite vector C here. And vector A. So the vector projection of C onto A is, we said the dot product between C and A. So negative 8 times 3 is negative 24. 0 times 1 is 0. Negative 2 times 2 is negative 4. Okay. A dot itself, 3 times 3 is 9. 1 times 1 is 1. Negative 2 times negative 2 is positive 4. And the direction we're following, or we're collinear to vector A. So that'll be negative 28 for the dot product. So again, we have an obtuse angle there. Over 14 times vector A. This cleans up really nicely. It's just negative 2 times vector A. And actually, I'll write vector A now. 3, 1, negative 2. So the vector projection is negative 6, negative 2, and positive 4. So those are our scalar and vector projections. So again, your scalar projection is just the shadow that one vector casts on the other vector. It's just SOHCAHTOA or manipulating your dot product. Nothing actually new. And the vector projection is just combining that scalar projection with a unit vector of the vector that you're projecting on. That's it.